Okay, so here we're looking at a problem that has to do with the rate of change. A conical tank, so conical tank, we're dealing with something that has the shape of a cone with the vertex down. So this implies that we have something like this. And then if we take this to be the central axis, so we have this. So let's take this to be a rough sketch of our cone. Vertex is down. Has a height of 10 meters. So they're telling us that from here, the topmost point, the bottommost point, the height is 10 meters. Next, radius, the top radius of 4 meters. So the radius from here to here, we have 10 meters. Sorry, 4 meters. The radius is a 4 meter. If water is leaking at 0.3 meter cubic per minute, so this is the first hint that you have, 0.3 meter cubic per minute. This tells you the expression you need to concentrate on. When I look at this, this is volume based on the unit there, meter cubic. This is volume per minute. So volume was differentiated with respect to time. What this implies is that I need to get the expression for the volume of a cone. Okay, so by looking at what we have here, we need to get the expression for the volume of a cone. Because we're seeing that is a meter cubic. So how do we get the volume of a cone? The volume of a cone is obtained by multiplying 1/3 pi r squared times the height of the cone. This is the expression that gives us the volume. I want to get a derivative. The question continues to say, how fast is the water level dropping when the depth is at 5 meters? So we see that as the water is leaking out, the volume is changing. So the volume will be changing. And as the volume changes, the radius will be changing and the height is changing. So as it stands, this is a variable that depends on these two. So we don't want to have two variables here to be controlling the volume. We want it to only be one. So we need to find a relationship between R and H so that we can let or write one in terms of the other. So since we're going for when the height is at 5 meters, so what do? We're going to picture that point. When height is at 5 meters, we're going to be dealing with something like this. And we'll not say that this is when the height is at 5 meters. We can actually just say this is at a random point. Let's say this is at a random point as the volume reduces. At one point, it will be at some random point. The radius will be at some random point, small r, and with the height, small h there. So when you compare the triangles for when the volume has reduced to, say, this level, when we compare this to when it was originally at that level, we see that the radius when the volume has reduced compared to the radius when the volume was initially complete, when the cone was full, this ratio has to be equal to the ratio of their heights. The height after the reduction occurs over the height initially before the leak started. So this is what we should have. From here, we see that we can actually compare or express the radius as the ratio of the heights times the original radius r. Now, what this gives us is what the radius is going to be at any point, provided we know what the height at that point is. So the original radius here is 4, it's a fixed value. The original height is a 10, it's a fixed value. The original height being this, and the original radius being this. In the end, we see that the radius of the cone for the water in that cone will be given by, when we divide this, since the original radius is 4, this is going to be 2/5h. This is the expression that gives us the radius. So at any point here, we can get what the radius is going to be, but our goal is not to know what the radius is. It was to eliminate the radius in this expression. And now that we have the connection between the radius at any point in time to the height at that point, we can get the expression for the volume. The volume now, depending only on the height, will be 1/3 pi. Where there is radius, we'll put 2/5h. But the radius has to be squared with an h there. So you can verify the radius in the problem. Total radius is indeed 4. And then we're going for the depth of 5 meters. So the depth of 1 meter. When we simplify this expression, we end up with 2 squared before. So 4 pi over 5 squared will be 25. 25 by 3 be 75. I hope you guys are going through what I'm doing here. Just make sure I don't make any errors. So you have 4 pi, 25, 25 by 3, 75. And then h squared by h to the power 3. Is this all right? Now we can get how fast the volume is changing. So the rate of change of the volume was given as 0.3 meter cubic per minute. This is how fast the volume or the water was leaking out, 0.3 meter cubic per minute. So let's account for that. When you do differentiate the volume with respect to time, now that we only have one variable, which simplifies our work here, we'll differentiate this whole part is a constant, 4 pi over 75. When we differentiate the h to the power 3, since it's also a function of time, we'll differentiate it implicitly. The 3 will multiply here, the power reduces by 2, and then we'll multiply this by dh dt. So from here, we now have to simplify this. 3 and 75 will simplify. So this becomes 4 pi h squared over 25, since 3 will go 25 times into 75. From here, we've been told what the rate dv dt is. That's 0.3. So don't forget it's 0.3 meter cubic per minute. So it's coming with a per minute there. So I'm going to have 0.3 here is equals to 4 pi h over 25. What we're looking for is how fast the height is reducing. So how fast is the water level dropping? The water level is determined by the height. So from here, we have to make the dht, which will be how fast the water level is dropping. So when we cross multiply, dht will be equal to 0.3 by 25 over 4 pi h squared. We're looking for this rate at a given point when h is equals to 5 meters. So when h is equals to 5 meters, what will this be? So we'll have 0.3 by 25 over 4 pi multiplying the height squared. The height squared, that will be 5 squared. 5 squared is 25. So this and this will cancel, leaving us with 0.3 divided by 4 pi. What will this be? So that's 0.024. The units, since the volume had meter cubic, so this it was meter cubic per minute, that was the volume. So since this is the height, with this with time, this will be meters per minute. This is how fast the water will be reducing.